Peace. Hotep, hotep. Hopefully everybody can hear me or I can be heard if I'm in here by myself. So just checking my levels. So let me start right off and say peace to anyone who has clicked and tuned in to me. You know, I do these Facebook Lives out the clear blue sky at any given times. But at least for this particular one, I gave a little bit of forewarning on what I intended to do. I didn't give a time, so you know, that's just the nature of how I go live, due to, you know, other things that I'm involved with. So um, today I'm going live to touch on a subject based on a Facebook post that I did recently. And the Facebook post that I did was entitled, was my statement in the post was that, believe it or not, full blood siblings do not have the same ancestors. All right. And so if you go on my timeline, if you're my Facebook friend, then you probably saw it, or you can go on my timeline and you'll see the post. It's a recent post, maybe 2 posts ago. And and I posted in on my timeline and in another Facebook group, and it caused a little um friction between some of the comments. And I just wanted to, I'm going live now to kind of clarify uh what I'm saying, the claim that I'm making, and the points in support of it. All right. So I'm just going to stall a little bit to give anybody a chance to tune in who saw my, what do you call it, my for warning that I was going to go live tonight, and who may have been looking forward to chiming in. All right. So, and also in the meantime, I'm going to post a link to come in, and if you have some thoughts about this subject, or questions, or anything, maybe information to the contrary, you have something to show where I'm erring, then by all means you're more than welcome to come in. So I'm gonna post a link in the chat after I'm done just presenting some basic information to support my statement. All right. So I want to get past that first, and and do this video as an archive. So when the subject comes up, I'll be able to link people to this video. And if you know anybody that was interested in this based on the conversations in the post and in the comments, then, you know, uh, make sure you give people the link in terms of this video, this conversation now, or even later in the archives. All right. So if someone could do me a service and type into the chat of this video, if you're watching, that I can be heard. I always like to make sure. If someone could do, I seem to be, things seem to be fine, but I just want to make sure I want to at least be able to see the chat. All right. The comments. So if someone could type a comment and let me know. Okay. All right. So peace to Fitz Yogi. Fit Yogi. Hear me. All right, good. Okay. So there's a few people watching. You know, like I said, I kind of go live out the clear blue sky. So I'm not, you know, doing this, you know, anticipating a large crowd or anything like that. But for the sake of the video and to have it on Facebook to be able to direct people to it on this subject is good enough for me. All right. So I'm just going to dive straight in. Now, I posted this again on my timeline, the topic, and I posted it in a Facebook group. Okay. And so for the most part, people found it very interesting. And but then there were a few people who said I was wrong about what I was saying. And, you know, I welcome the discussion. And if I'm wrong, you know, I want people to explain where I'm wrong and how I'm wrong. All right. I welcome that. And so hopefully, you know, those people will be able to tune in and chime in on the conversation. But I'm just going to dive in and explain it. So hopefully those who are watching now, I'm a person who likes crowd participation. I like interaction, that is. So I'm going to monitor the chat when I can. And if you have, something to say or anything like that, make sure you type it in the chat. And I'm going to post a link for you to come in and actually chime in with me once I'm done laying a quick foundation. All right. So having said that, let me go to the post. All right. So I'm just going to show you all my post. And let me get my cursor over here so I can. Okay. So this is my post, and I shared it in a Facebook group. So I'm just going to read my statement. So I say, believe it or not, full blood siblings do not have the same ancestors as each other. Then I have a hashtag DNA recombination and Imam Wujau. All right. And so, people know me. I do these posts because I invite discussions, progressive, beneficial discussions on different topics. And so this is one of them. All right. So people found it very interesting, and they, it's kind of hard to believe. Like, wait a minute, full blood siblings don't have the same ancestors. What are you talking about? You are out of your mind, Ujao. So if I scroll down, now this is shared in the group. So if I scroll down in the group, I'm just going to share a couple of the comments real quick before I present something. So Dale Lewis says, I always had an issue with recombination. I'm not informed enough to have a discussion, though. And then a brother by the name of Sean L. Williams. As a matter of fact, this brother, Sean L. Williams, I specifically invited him to either check out this video live that I'm on right now, or he'll see the archive, or even in the future, if the brother's available, to have a discussion, a real-time discussion with me, because of a couple of comments that he made on the post. So he first asks, how is this true? And then a sister by the name of Lakeisha Felton says it's not. And see, so here's what happens. People will ask questions or make statements, but then don't give any information. It becomes just chit chat, and that's fine to an extent, but it's not helpful at all. Just to say it's not true or it's not. Okay, well, what about it's not true? So then the brother comes back and says to her, Lakeisha, and says, I was wondering if or hoping there was some tricky punchline to this post. I see now that it's just another, I guess he meant insane or inane post from someone who does not know what the F he is talking about. And see, it's because of this comment right here that I specifically invite this brother, Sean L. Williams, to come on in real time with me to show me just how much I don't know what the F I'm talking about. All right. So we can have a dialogue and see between us two who knows what they're talking about and who doesn't. All right. So that's why I specifically invited this brother onto this session. So once I've finished laying down some brief information, I'm going to check and see if the brother's in the chat, and he's more than welcome to come in. But that was his comment. And then the sister goes on to say, I just want people to be clear in what they want to convey. I hate when people post blanket statements as fact, but when you challenge them on it, they want to pivot and say that's the post was meant to generate an adjacent discussion. How, Sway? How are we supposed to know that? Make it make sense. Be clear in what you want to talk about. The failure of a person to understand the conversation is not on the person who is confused, but the person who has conveyed the message. This is definitely a shoot the messenger situation. The messenger failed. All right. So basically, what she's saying is that I posted what I posted. She challenged me on it, and then she implies that I posted this for an adjacent discussion. And anybody that knows me know I never do that. I'm a person that's a stickler for staying on the topic. I don't even want people to come on my post, uh, diverting the conversation on any other topic other than what I post. So this is just not true. It didn't happen, and the sister is definitely making it up. So again, She doesn't say how it's not true at all. All right. And then Sean comes back and replies to her. So I'm not going to read it all, and I'm just going to skip around. But I just want to show. So later on, I give another comment, elaborating a little bit, and I give a link for people to read up on, to check out, so that they can be informed to chime in on the discussion. And um, so after doing this, there's some more comments, and based on the comments after it, I can tell, you know, people did not click the link and did not read it. All right. So I had to post it a couple of times. So, again, I'm going to skip, and I'm just going to explain. But here's the sister. So let me at least go to her. Um, so Lakeisha Felton says that is not what DNA recombination means. So this is her statement. So let's go back to the post. This is what I say. Believe it or not, full blood siblings do not have the same ancestors as each other. And I have a hashtag here, DNA recombination. So she's saying that that's not what DNA recombination means. Now, see, at no time in my post do I define DNA recombination. So I let her know that, but let me finish reading her next comment. She goes on to say, full-blooded siblings absolutely have the same ancestors. DNA recombination in simple terms means that your DNA recombines with every generation. And that's not true. So she obviously doesn't know the definition of DNA recombination. All right. Um, that's not what it means. And I'm going to show you all that. So she's saying that I'm wrong. And then she said that's not what it means. And then she gives an incorrect definition of DNA recombination. She said, you only inherit roughly 50% of your DNA from each parent, 50 from dad, 50 from mom, which 50% you receive is random. If we all receive the exact same 50% from each parent, we'd all be identical twins to our siblings. All right. So that's her comment. So then I address her and I say the intent of the post is to discuss the consequences of DNA recombination, not to define it. But in gist, so then I help her out, and I tell her that in gist, DNA recombination involves the exchange of genetic material either between multiple chromosomes or between different regions of the same chromosome. That's what DNA recombination is, not what she said. All right. Then I go on to say that full-blooded siblings absolutely do not have the same ancestors. Approximately 50% that two siblings receive from dad or mom is not the same set of 50%. As a consequence of this, two siblings may not inherit the same ancestral DNA. This is more apparent as you walk back through the generations. For more information, see, and then I give her the link. And so I'm going to stop there, but anybody can go to the Amara Squad Facebook group and read more of her comments and other people's comments. All right. But those are the comments. All right. But I don't want to take too much time reading comments. All right. So now let me just go to information. I just want to lay out some information about what I'm discussing. So let me just repeat what I stated. So again, I say, believe it or not, full blood siblings do not have the same ancestors as each other. And just real quick, let me just see if I can see you all. Whoever's watching, that is. So based on my statement, whoever's watching me now, if you can, if you don't mind, typing into the comment section, the chat right now, how many of you all find that hard to believe that full blood siblings do not have the same ancestors as each other? So let me just get an idea of where you all are right now. So I know there's a slight delay, so I'm gonna kind of waste a little time here to see who responds. And by the way, peace to whoever is watching me right now. Would give a shout out if you all typed and I knew exactly who you were, but I can't tell. So, and I don't know. So I'm gonna wait a little while, not too long. Not too long, not too long, not too long, not too long. All right, so I'm not sure if I'm gonna get any replies, but I do see people are watching. All right, now don't be scared now. Hope nobody's scared or intimidated, because then of course, then when I post the link, if anybody want to chime in, what's the use if I can't even get anybody to comment? All right, okay, so I'm just gonna jump into it. All right, okay, so listen. All right, so if you all find this hard to believe, now if you're checking this out in the archive, you can. Well, obviously, you're not going to hear me say this, but you fast forward to this point where I'm going to present some information. All right. So remember what I'm saying. Full blood siblings do not have the same ancestors as each other. So how? How is that, Wujao? How is that? All right. So I'm going to jump into it. All right. So now, in order for me to kind of illustrate this is the a very short, condensed way that I can illustrate this without going through several generations and showing details of the generations. What's passed down through generations. All right, so um, everything I'm saying holds true, but I'm doing a very condensed version. All right, in my illustrations. All right, so to begin, to start things off with, we're going to start with a man and a woman. All right. And the dad or the man is the dad, the woman is the mom, obviously having a child. So the dad is represented by 4 blue circles. The mom is represented by 4 pink circles. Okay. So when they have a child, the child gets 50% of their autosomal DNA from their dad. And it's approximately 50% because not exactly 50%, but everyone pretty much rounds it off to 50%. So I'm just letting you know that. So if you do your research, you'll find that it's not always exactly, or it's actually rarely exactly 50%. But 50% comes from dad, 50% comes from mom. All right. Now everybody can clearly understand that. This is a no-brainer. This is what everybody pretty much understands without any further research or anything like that. This is not rocket science. Okay, so what I'm starting out with is a dad and a mom giving birth to a child. Okay, so this is the child of these two. So you see blue and pink with the child. Now we have another couple. All right. So this is a second couple, another man and another woman, represented by green and yellow. So when these two people come together and have a child, their child will be a combination of these two parents, green and yellow. All right. So we have these two children. Now, to continue. So what I'm going to show now is these two children, the children of these two couples. So I've shown 2 couples so far. This couple and their child, and this couple and their child. Okay. So this is what I'm showing here. So this is the first couple. All right. The blue and pink and their child, which is blue and pink. Then I have the second couple, which is green and then yellow, and then their child, which is green and yellow. All right. Now, so this is a generation, and then this is another generation. And now we're going to give birth to a third generation. So we're looking at 3 generations here. So now these two people come together, dad and mom come together and have 3 children. All right. So I want you all to pay attention. This is child number 1. So the 50% that this child gets from dad happens to be the blue, okay, and not the pink. The 50% that this same child number 1, gets from mom is the green and not the yellow. Okay. So mom and dad produce child 1. This is the big brother or big sister. All right. And this is what this child inherits: the blue from dad and the green from mom. Then they have another child. They have child number 2. Child number 2 gets the pink from dad and the green from mom. Okay. And then child number 3 gets the pink from dad again, but the yellow from mom. All right. So now, what are the consequences of this? What is this telling us and showing us? This diagram here is a visual representation of my statement. All 3 of these children are full blood siblings of each other. They have the same parents. That's what full blood mean. I don't mean identical twins. When I say full blood siblings, I mean siblings that have the same mom and dad. All right. So these 3 children have the same parents. Now, my statement is that full blood siblings do not have the same ancestors as each other. And so this is demonstrating this visually. All right. So look at child 1. Although child 1 gets 50% from dad and 50% from mom, what's not in child 1 are the pink circles that came from dad's mother. Okay. Dad's mother, which is this child's grandmom, was not a contributing, did not contribute any DNA to child number 1. So grandmom, and mind you, I want to say this disclaimer. I am condensing generations because in 3 generations, what you're seeing is likely not to happen so quickly between these generations. All right, between only 3 generations. So again, I'm condensing generations to make my point. The point holds true. It would just take me a whole lot longer to go up 16, 6 to or more generations to illustrate my point. And plus, I don't have room on the screen. All right. But the point should be very, very clear with these colors. So child number 1 has no DNA from grandmom, but yet grandmom is that child's grandmother. That doesn't change. But the grandmother did not contribute any DNA to that child. All right, let's move to child 2. Child 2 has the pink from dad and the green from mom. But guess what? This child's maternal grandmother, which is the mom's mother, this child's maternal grandmother didn't contribute any DNA in child number 2. All right. Likewise, this child number 2 has no DNA contribution from that child's paternal grandfather, which is granddad. So none of granddad's DNA is in this child, and none of his paternal granddad, and none of his maternal grandmother's DNA is in this child. Okay. So, but this child has grandmom, this child's paternal grandmother DNA and maternal grandfather. But this child number 1, did not. So child number 2 has an ancestor that child number 1 does not. And child number 1 has an ancestor that child number 2 does not, but yet they're full blood siblings. And it's still all part of the same family. Okay, now let's move to child 3. So child number 3 has 50% from dad, which are the pink, 50% from mom, which are the yellow. But it doesn't have the blue that came from granddad or the green that came from, the paternal granddad, nor does this child have the green from their maternal granddad. Okay, it's missing. But yet all of these are siblings. Okay, so the maternal granddad is not an ancestor of child number 3. All right. The paternal granddad is not an ancestor of child number 3, but they are an ancestor to child number 1. Hence, and the point that I've made is that although you can be full blood siblings of to each other, you do not have the same ancestors as each other. All right. So this diagram illustrates my point. And mind you, I do understand that this is a very condensed. When I say condensed, I mean generations. I'm only showing 3 generations to illustrate this point. But in reality, what I'm showing would span more than 3 generations. Okay, so I'm just letting you all know that. All right, so the question now should be, how does this happen? Why does this happen? All right, and so this is due to what I um, put in my post as a hashtag: DNA recombination. This is why and how it happens. All right. So I'm going to show that. But let me pause for a second because I can't see the screen if anybody has any questions. But I'm going to come back to this. So let me just finish explaining, because like I said, this video will serve its purpose as an archive to refer people to it. All right. So I'm just going to continue. But hopefully that's very clear. All right. Now, so how does this happen? So let's go back. Let's go back. Let's dig into, human biology. All right, a little bit. Stuff that we didn't pay attention to in school, or in school, grade school, they don't really dig in, go in too deep with this information. All right, so now what I have on the screen now is your typical human male. All right, this is a human karyotype. And a karyotype simply means the number and the visual representation of the chromosomes. Okay, so we all know that human beings, we have 46 chromosomes, and they're broken up into 2 pairs. So, 23 pairs. So there's a pair of chromosomes each, adding up to 46. So we have 23 pairs, and that's where companies like 23andMe get their name, the inspiration for their name. They're talking about the 23 pairs of chromosomes, totaling 46. So here's your typical karyotype for a human male. All right. So you have chromosomes and they're numbered 1 through 23. So quickly, 1 to 22 are referred to as autosomes. All right. So these are our autosomes. The 23rd chromosome pair are our sex chromosomes. You'll see that in all of the literature, sex chromosomes, because it's the 23rd pair that determines your sexual gender. If it's an X and a Y, then you're a male. If it's an X and X, it'll be a female. So this is the male, all right? And here are the chromosomes here. So I'm going to illustrate that. And this is your typical female or woman, human karyotype. Same 46 chromosome, 23 pairs, but except the 23rd, notice here it's the X and X. For the male, it's the X and Y. Okay, so that's the only difference between these two images. All right. So now we know that as human beings, we have 46 chromosomes. So when a man and a woman come together and have a child, that child also has 46 chromosomes. So each human being has, with their 46 chromosomes, they get one set, which is 23 from their mother, and they get 23 from their father. All right. And this 23 and 23 is where you get this 50%. So you get 50% from your mother, you get 50% from your father. That's not rocket science, that's straightforward. But now here is where it is a challenge, and what people may not know, because this is not something that's generally discussed in everyday conversations. All right. Everything I said so far, we pretty much know that. We know we have 46 chromosomes, et cetera, et cetera. But now when you have a child, what happens is that the mother and the father don't pass down these chromosomes in large chunks, like as you see on the screen. That's not how it works. Okay. This is how it works. And this is why I put as a hashtag DNA recombination. All right. This is actually what DNA recombination is. It's also called crossover. Okay. When chromosomes cross over. So if you do your research, which I encourage you to do, and you look in the literature, you're going to find it being called crossover or recombination. All right. So that's why I have both of those on the screen. So this is what actually happens. Now I'm taking chromosome 1 from the man just for illustrative purposes. Okay. So I'm only dealing with chromosome number 1. Remember, there's 23 of these pairs, but I'm only using pair number 1. And from the woman, I'm only going to focus on chromosome 1 from the woman. Okay. So chromosome 1, what you see here, from the man, and chromosome 1 from the woman. So I changed these colors so I can illustrate the point here of actually what the process happens. Now, when a man and a woman come together and have a child, the child receives only one set of the pair, only one of the pair from the father, and only one of the pair from the mother. So, in most people's minds, what that would mean is that the child, there's a choice between the blue in this example, between the blue and the yellow. So that means the child would get either the blue or the yellow. And same thing for the woman. The child would get either the pink or the green. I mean, that makes sense, but that's just not how it happens. What happens is prior to the chromosome being passed down, these chromosomes combine. Okay. They shuffle or they combine. And so what happens is that certain segments of the chromosome pair, this is a pair, they will cross each other. That's why it's nicknamed crossover. They will cross over and form a new chromosome that's unique. Okay. So this is why I have represented by this top portion. So the top half crossed over and became yellow. So the top half is yellow and the bottom half is blue. And that's what the child inherited. Okay. And likewise for the mother, the top half is green and the bottom half is pink. So this is actually what the child receives, not a full blue or a yellow, and not a full pink or a yellow. All right. This is called recombination. This is what happens or takes place um when a child is conceived. All right. So now to further elaborate, I'm going to go back to the man. So this is the chromosome number 1 from the man again. All right. And so this man's chromosome number 1, how this particular man got his chromosome in the first place is from his parents. So from his dad, his mom, and his dad. Okay. So this is how his chromosome number 1 looks. Okay. So the one on the right, he inherited that from mom. The one on the left, he inherited that from dad. Okay. So now I have these colors here for a reason. So he inherited from his dad a chromosome that has yellow in this segment and pink in this segment. He inherited one chromosome um, from his mom, where this segment is red and this segment is black. All right. Both of these chromosomes is chromosome pair number 1 in this particular man. All right. So I need, I'm trying to make sure that you all are following what I'm saying. Now, what happens when in human reproduction, these chromosomes are not passed to an offspring wholly like this. Again, they go through a process called recombination where they cross over. And so a single chromosome is produced from these two pair after crossing over, after mixing, okay, or combining. And so out of these two, this chromosome, this single chromosome is produced. And this chromosome, the single chromosome, which is chromosome number 1 from the man, is what is within the sperm cell. Okay. Now I want you to notice that it received the red segment from dad, from the man, and it received the pink segment from the man, but it omitted the yellow and the black. So when these two pairs combined or recombined, the outcome was red and the pink one. The yellow and the black were omitted. Okay, so I want you all to bear with me. So this is what the man will contribute to the child on chromosome number 1. Now we're going to do the same thing for the woman. So here's a woman and her chromosome pair number 1. These are her pair. So you see the segment, she has a blue and a green. This left chromosome she inherited from her father. And this right chromosome she inherited from her mother. On this side is black and green, black and light green. So we have a blue and I guess a teal color, and black and green. Okay. So when these two chromosomes recombine or cross over, as it's called, the outcome is this single chromosome that is found within the ovum or egg. Okay. So the black crossed over, not the blue, and the teal crossed over and not the bright green. So what's included is the black and teal. What's excluded or omitted is the blue and the green. Okay. And so this is contributed to this is in the ovum, and this is chromosome number 1 that's going to come from the woman. Okay. So again, let me back up. This is the outcome of chromosome 1 that the man will contribute, and this is the outcome of chromosome 1 that the woman will contribute, but only after a process of recombination. All right. So now let's go to the next step. So this is what happens. Now I'm showing on the screen the chromosome pair number 1 from the man and the woman. So I'm repeating what I just showed. So the man's chromosome number 1 pair is here. It's going to produce this chromosome, the single chromosome in the sperm. The woman, this is her chromosome pair number 1. And after recombination, it will produce this single chromosome in the ovum. Okay. So both of these will be inherited by the child. So this will become the child's chromosome number 1 pair. Okay. This will be the pair. So you got the red and the pink from dad right here. You got the black and the teal from mom up here. Okay. So that's how the process works. That is to explain how DNA recombination occurs. This is what happens with every single human being. The only exception to this is when you have a case of identical twins. All right, to the statement that I made that full blood siblings do not have the same ancestors as each other. The exception to that would be identical twins. And hopefully you can see why by me explaining this process of recombination. But let's continue. So this is, let me go back. This is the result of child number 1. All right. Now let's step back. What do these colors represent? Let's make these colors here represent segments of DNA that was inherited by ancestors. So I'm going to go back up again. All right. So we're going to start here. So remember, this is our man. This is the man. This is his chromosome pair number 1. He got this left side from his father, and he got the right side from his mother. But let's say that the yellow is the yellow was inherited from this man's 3rd great grandfather. So this yellow represents his third great grandfather, a segment from him. And this red represents that he got from his mother, represents a segment from the fourth grandmother, okay, generations previous, and so on. But now here's the thing. When this man passes on his chromosome for his chromosome 1 after recombination, guess what? The yellow segment is omitted. And mind you, what I just say, this yellow segment came from this man's third great grandfather. So guess what? This child who is going to receive this chromosome is not going to have genetic material or DNA from this man's third great grandfather. It's omitted. Okay? So we can do this for any of these colors, but I'm doing this now to illustrate that these colors represent DNA contributions from previous generations within this man. Okay. So immediately there are two ancestors that are going to be omitted. Whoever this black segment came from and whoever this yellow segment came from, they're no longer present in the offspring. Okay. Due to recombination, even though it's present in this man, it's not going to be present in the child. Okay. So that's what this is showing. So each of these colors here represents a previous ancestral contributor to this man's DNA and this woman's DNA. And so after recombination, they pass on a single chromosome, and she passed on a single chromosome for chromosome 1, and it forms a pair in the child over here. There are omissions of ancestors. Now, mind you, this is child number 1, the chromosome pair for child number 1. So the yellow is missing. We don't see any yellow. That's over here. And for the woman over here, we don't see any blue and we don't see any bright green. So blue and bright green is missing from the child, and the yellow is missing from dad. Okay. So those are non-contributors. So those ancestors didn't contribute any DNA into this offspring, child number 1. Okay. I hope I'm clear on that. Now let's do the same thing for another child. This same couple, okay, this same couple has another child. This is child number 1. So the same couple is going to have another child. So this is the man again. Same chromosome pair, same colors. But this time, when these two chromosomes recombine, the outcome of it is yellow and black. The red and pink are omitted. Okay. Now this is in the sperm. Okay, this particular sperm cell. All right. And the woman, likewise, when her chromosome pair combine again for another ovum, another egg, now it has, for chromosome number 1, it has blue and bright green, no longer the black or the teal. They're omitted. So what is this child going to inherit for chromosome 1? In this illustration. So now we have child number 2 inheriting from mom and dad these two pair of chromosomes from mom and dad, respectively, from dad and then mom on the right. Okay. So what's missing? The red and the pink from dad. It's not here. What's missing from the mom? The teal and the, what color is that? Black is missing from mom. So whoever contributed this DNA segment to mom, whatever ancestor that did that, the child is not getting it. That ancestor is not in the compositional makeup, DNA makeup of this particular child, number 2. So what are the consequences of all of this? This, again, supports my point and statement and claim that we have two parents here. They have two children, okay? So this is the man and woman here, right here. Chromosome 1 from the man, the pair, chromosome 1 in the woman. They have 2 children. This is child number 2, and over here is child number 1. Okay? So notice they have the same parents, but look at their chromosomes. Child number 1 has omitted ancestral DNA contributions that child number 2 has, and vice versa. So, again, to reiterate my point, these 2 children, although they're full blood siblings, they have the same parents, they do not have the same ancestors. All right. They do not have the same ancestors. And this is how that occurs. It happens all the time. And so what this should illuminate with everyone is that our idea of ancestors. Now, let me say this. In regular everyday parlance of how we speak about ancestors, usually and generally the word ancestor simply means a deceased person, somebody who has died. Okay, in general, that's the broadest sense of the word of how it's used in everyday speech. Okay, more specifically, even in everyday speech, um, an ancestor is a person who is a family member that has passed away. All right, or a person who's from a previous generation. Okay, that's how the word is used in general. But now, in a discussion about DNA, genetics, and things like that at the DNA level, the word ancestor takes on a new meaning. And this is what I recently posted on Facebook. Ancestor has a different meaning in this level of a conversation, and we have to understand this. In this context, an ancestor is a DNA contributor to a successor. Okay, that is your ancestor, not just a ancestor or an ancestor, but that will be your ancestor. Your ancestors are those who contributed to your DNA composition. Now, again, it does not mean that people in previous generations are not part of your family tree or family genealogy. All right. Like I showed here, let me go back. When I showed this example here, child number 1 has no contribution from his paternal grandmother. Now, does that make this person no longer this child's paternal grandmother? No. This person will always and forever be this person's paternal grandmother. But this paternal grandmother is not this child's ancestor, DNA ancestor on the level of DNA. Now, like I said, the way that we use ancestor in everyday speech and stuff like that, people will say, hey, that's my ancestor. Okay. Um, but the meaning behind that is that, okay, this is a person that is in my genealogy, my family tree, and, this is my dad's mother. But she is not this child's ancestor, DNA ancestor at all. So what that tells us is that people can be in your lineage, but not your DNA ancestor. And that sounds counterintuitive, but it only sounds that way because we don't have a we don't normally speak about the process of inherited, DNA and how it's inherited through the chromosomes. We don't normally discuss things like that. We don't talk about DNA recombination. And I and in having these discussions myself personally with other people, I've been finding that a lot of people don't even know about it. They don't even know that it occurs at all. Like they've never heard of it, because the idea is that, okay, we all have 46 chromosomes, and I get, 23 from my mother, I get 23 from my dad. And that's it. But nobody really, looks into how do I inherit it? In what way? What is the process? Okay. So once you look at it, you'll understand how this makes sense. So we can have family in our lineage that are not our DNA ancestors. And this is why when people get DNA ancestry tests done, siblings, they come back with different results. And they're so-called ethnic estimates. The ethnicity estimates between siblings will not be the exact same for this reason. And people come, I've seen people on Facebook ask, well, why? And see, people assume that the ancestry companies are scams. They're like, oh man, see, me and my sister, we took a test, or me and my brother, two males, me and my brother took a test and we came out with different results. Ah, see, and I know that we're full blood. So that company's a scam. It's just, it's just novelty. It's just scamming people and this, that, and other. No, that's not why. And they're not scamming for that reason or nothing, you know. It's because you just don't understand how DNA is passed down. Okay, so hopefully this will clear that up. But again, I just want to illustrate this and demonstrate my post and my claim. All right. So hopefully that's clear, because I don't want to make this longer than I have to, but this is the outcome. So again, let me just summarize here again. So we're starting off with a man and a woman. The man is represented by these two blue chromosomes and the woman by these pink ones. Okay, this is only on chromosome 1, because mind you, remember I said there's 46, so there's 23 pairs. I'm only focusing on chromosome 1. Okay, so the man's chromosome 1, this is what it looks like. He has 4 segments from 4 different ancestral contributors to his DNA. Likewise, the woman, she has 4 ancestral DNA contributors to her pair, okay, represented by these 4 colors. When she passes this chromosome down to her child, it's going to first recombine or cross over. That's key to understand that. And I encourage you to look that up to read about it more. Before passing this down, before this becomes part of her ovum, that's going to later be fertilized by a sperm, this is recombined first, and then a single chromosome is passed down. And when it recombines, by the nature of recombination, some of these segments are just going to be excluded and some of them are going to be included. Okay? That's how it happens. And so she passed down to child number 2 her black and her teal. But in child number 1, she passed down her blue and bright green. And mind you, like I said, these colors represent segments coming from ancestral contributors. So hence, or thus, the point that I'm making and I'm demonstrating is that 2 siblings, although they're full blood, they do not have the same ancestors. All right. So that's all I wanted to demonstrate and touch on in this live here. But what I do plan to do, what I do plan in the near future is I'm gonna explain this again. I'm gonna go live again, but at a much better time, because I want people on a panel for this discussion. I'm gonna have a panel discussion about this. I'm gonna go over this again, but I want to extend the conversation to answer or discuss the question, what implications does this have on our ideas of ancestral veneration and ancestor worship? Okay. And that's going to be a very interesting conversation that you don't want to miss out on or chime in on. All right. So I'm going to have a panel discussion about that. What does it mean to worship an ancestor? What does it mean to venerate an ancestor, or your ancestors? And do my ancestors differ from my siblings' ancestors? We already know the answer to that. So when I venerate my personal ancestors, it's going to have to be different than what a sibling of mine does, etc., etc. So what are the implications of all of this? You know, so that's going to be a more extended discussion I would like to have. So anyway, but I'm going to kind of end this here. And if anybody's watching, so what I'm going to do right now, I'm going to post this link. If anybody has something to share or speak on, I'm going to post this link into the comment section. And there it is. And I'm going to pin it. So I'm going to take some time, you know, if anybody comes in, take a little bit of time to have a discussion, a quick discussion. If not, then hopefully what I've shown so far demonstrates the point that I'm making. And if anybody has something to the contrary to what I'm saying, then now's the time to speak up if you're watching. And if you're watching in the archive, then obviously you could type in the comments, and then hopefully you'll join the discussion when I do this again. All right. So, and peace to everybody. Peace to Fit Yogi again. Greetings. Peace to Mika, Monica. I got Mika, Monica. I'll call Monica Whoop Whoop. Kuta Khan, Hotep. And that's all I see right now. And we have Emicat, of course. So anyway, don't be scared. Now, don't be scared. Now, Mika, I know you watch all these different presentations and shows and everything like that. Go on and click the link. I know you have some questions. Click the link. Go ahead and click that link. Just click the link. I know you have some questions because you actually asked how on the post. So, you know, hopefully I answered that for you. And if you click the link, and you know, if it's still not clear, or you know, still seems far-fetched, go ahead and click the link. What I should have done was share this, you know, in the other group as well. But like I said, it's late, you know, and I jumped on late. So, and plus it was semi unannounced. Okay, she said I'm absorbing the information. Okay, all right. So, man, for the first time, Mika is oh, you might be at work or something, huh? Because I'm surprised you didn't click the link. Because Mika usually like, I got a question. I got a question. You mean to tell me that my ancestors are not my ancestors? Now I gotta rethink the whole ancestor thing. Well, Joe, you making up definitions. That's not what my dictionary says. Ancestor is an ancestor. Is an ancestor is an ancestor. All day, every day. No, but all right. So let me, since nobody clicking on the link, let me just summarize again, right? So listen, this is my claim and this is my statement. All right. Full blood siblings do not have the same ancestor. They do not share the same ancestors as each other. Okay, that's my statement. All right. I can support the statement. I'm showing it, you know, in the best way I can in this, you know, brief amount of time visually. But I can't do the homework for you. So I don't want you to just listen to what I'm saying and say, okay, whatever Wujao says. No, don't do me like that. Go look this up. You know, look into this. And I'm pointing you in the direction to where to look. You're gonna have to look up DNA recombination, or what they call crossover. So remember this, always remember this. We have 46 chromosomes. We get 23 from our mom and 23 from our dad. And our mom and our dad had 46 each within them. But guess what? Each pair, we don't just choose one of the pair. One of the pair just doesn't pass on to the child or to us. We don't inherit just one, any, meeny, miny, mo. No. What these pairs do before they're passed on, they go through a process called recombination or crossing over. Okay. So the pair will cross, segments of that chromosome will cross over, which means that certain segments will be omitted and certain segments will be included. And if a previous ancestor to your father DNA was on a segment that got excluded, guess what? That previous ancestor is no longer your DNA ancestor. Why? Because that person's DNA is not in you. Period. There's no other way that I can say it or put it. Now, on the post on Facebook, when I said it, obviously, if we don't have this understanding, then it's going to seem odd. It's going to seem strange. Like, oh man, that's not true. My ancestors are my ancestors. Why? Because people can't imagine that two human beings can create a child that therefore creates another child that becomes your father, and you not count them as your ancestor. That's counterintuitive. That goes against what would seem to be common sense. But that's not the case on the DNA level. And this is why we have to understand where this conversation is. This conversation is on the level of DNA. It's not on the level of the surface family tree. Of course, your 6-time great grandmother will always be your 6-time great grandmother. But guess what? That 6-time great grandmother's DNA may not be in you at all. Therefore, she is not your DNA ancestor, but she is a member of your family. You're a result of her. You're um, a descendant of hers, but she's not a. And that sounds strange to be a descendant, but yet not an ancestor, because you got ancestry and then descendants, ancestors and descendants. Those two words kind of go together in opposite directions. Ancestors go backwards in time, descendants go forward in time. So I get it. This seems a bit odd, but nature and the reality of what takes place paints a different picture. That's all I could say. All right. And again, if you study this and you find some contrary to what I'm saying, by all means, definitely let me know. I know you won't, but if you do, if you think you do, bring it to my attention and we can discuss it. All right. But think about this. The reason why, and I'm sure you've experienced this yourself or somebody. Have you ever had a sibling or you yourself, you obviously look like your parents a bit, but you ever noticed somebody who look like their parents a little bit, but man, they look like another distant relative, another relative in their generation upline. They look more closer to another relative. Well, guess what? The reason why that happens is because of DNA recombination. You may receive more quantity of segments of DNA from an ancestor, from a more distant ancestor than a more recent ancestor, because of this process. Because remember this as well, DNA recombination makes DNA inheritance like a lottery. It's random. The recombination segments, they're random. And this is the reason why we have diversity on the planet Earth right now. This is why there's diversity. Even within a population of people, there's a diversity. Even within a nuclear family, there's diversity. That's why brothers and sisters don't look exactly alike. Now, again, the exception to what I'm saying would be identical twins. And hopefully everyone understands why. And if you don't, just real quick, identical twins are a result. They refer to them as mono, I believe the word is monozygotic. Identical twins are monozygotic. They are produced from a single sperm and ovum that split and starts to generate two different children. And so their DNA are going to be the same. Why? Because the sperm. Now, mind you, hold up. Let me go back. Let me go back. Because let me put a chronology on this process. So again, I'm talking about the process, but let's go back to the man. Okay, so what you're seeing on the screen again is the chromosome pair number 1 from a man. Okay, now let's get into a little bit of reproduction a little bit. When women are born, they're born with eggs or ovums or ova already in their ovaries. Okay, they have lots of them, and really only, I believe, and somebody can correct me if I'm wrong because I'm going straight from the dome right now. About 300,000 of them are going to survive the lifetime. And out of that 300,000, only a certain percentage of that will actually go through the process of traveling through the fallopian tubes and going out through menstruation, et cetera, et cetera. All right, to be able to be fertilized, if that's the case. Okay. And with men, sperm is produced every day. Okay, every 72, approximately every 72 hours. Put it this way, it takes approximately 72 hours for a sperm to go through a maturation process to mature. All right. Now, why am I saying that? Is because this process that I'm pointing out, called DNA recombination or crossover, takes place prior to the formation of the sperm, or during the formation. So what you're seeing on the screen is the chromosome pair from a man that recombines, go through the process of recombination, and it ends up in the sperm at chromosome 1. Now, mind you, 23 of these are going to be in the sperm. I'm only highlighting one, chromosome number 1, but there's 23. So think about this. Every single living sperm within a man at any given time has a completely randomized um chromosome pairs. Not even pairs, excuse me, I'll take that back. Not pairs, but 23 sets of chromosomes. Every single sperm. And remember, you are a result of one of those sperm cells making it to the egg. There's a whole bunch of other ones that existed alongside you, but they didn't make it. But my point though is that this recombination occurs at the development of the sperm. So they're already there. Okay. So within a man and within a woman is a randomized set of ancestral DNA. And it's like a potluck lottery of which ones you will inherit. That's it. Now, again, I don't want you to just take my word for it now. I want you to look into this. There's a lot of videos. And if you need help, I could give you a lot of links on videos. I can recommend some books to you, whatever the case is. All right. That's why, when the sister said I'm wrong, I'm like, that doesn't, if somebody feels that I'm wrong, I welcome that, because I want to be, I don't want to pass on misinformation. I don't want to err, anything like that. Nobody wants to be wrong. So I welcome it. I welcome correction. I'm not going to get mad or feel any kind of way whatsoever. I actually get, I'm happy to be corrected. So when the sister said I was wrong, I'm waiting for the information. It's one thing to tell somebody they're wrong, but it's a whole nother thing if you tell them and show them. The sister never showed. Okay. The brother who said, I don't know what the F I'm talking about, never showed anything on the post. Now, I really wasn't expecting neither one of them to show up here tonight, because like I said, um, when I go live is random and it's late. So, I'm not, I would never hold that against anybody, if even if I invited them at a last minute or whatever the case is. So, I'm not, I don't do things like that. But on the post itself, the sister or the brother that said I was wrong, they never showed anything that I was wrong. Nothing at all. Offered nothing. And that's where it gets a little frustrating. People can't make empty claims, and then, they don't show anything. All right. Cause I'm not one of those kind of people that, if you say I'm wrong, I'm just gonna be like, oh, okay, I'm sorry. No, show me. Cause that's what I would do for you. If I see something, if somebody else is wrong on something, I'm gonna tell you, but I'm gonna show you. Cause it's not a competition. It's like, let's both stay on the side of accuracy and reality, real information. So anyway, I'm not gonna long this out. I was trying to buy some time, see if anybody wanted to click the link, but I see everybody's scared to click the link. Uh Fit Yogi, Chavis, Mika, peace to Sierra, Adams, and whoever's watching. I got 12 people watching. If you're looking for the link, I pinned it, so you should see it in the comments if you want to chime in. You have something to say real quick. And just in case it's not in the comments anymore, I'm gonna post it again for safekeeping. Buy a little extra 5 minutes. If not, then I'm gonna definitely close out. But so again, I'm gonna do this again. I'm gonna go over this information again, but I want it in it to be a panel discussion, because I want to extend the conversation on what are the implications of this on our idea of ancestral veneration and ancestral worship. Okay. Does knowing this information change that? Should it change it? What does it, should it give us a different view of it, or what? I want to have that discussion. All right. So yeah, and listen, if any of you all real quick, you don't have time or want to come into the Zoom call itself, if you have a question, type it. I can see the chat. I can see the chat. So type it out if you have something. You got 3 more minutes. Actually 4 minutes. Because at 12 midnight, I am definitely pulling the plug. So Mika, does it make sense to you now? I noticed the delay. So all right. Now let me just ask, has anybody had their first of all, has it if you have a sibling, a full blood sibling, have you had a DNA ancestry test done, you and your siblings? And if so, have they come back different from each other? Now I know it's not that many people here, so I probably won't get a yes to all of that. But if you know somebody, or if you in the future you actually go through that and you and your siblings do it and you come back with different results, that's going to be the reason why. Even from parent to child. So Mika, I know you have children, and I know you've done ancestry DNA testing. Now hold up, let me qualify that. Let me back up a little bit. Okay, let me back up. When I say that siblings have different results from doing ancestry tests, it has to be from the same company. And here's a quick reason why. Every DNA testing company, ancestry company, they have a reference database that they use. So when you send in your saliva and they map your genome, and they're gonna compare your DNA to their database. And these companies, they don't share databases, so they have a different reference data set from each other. Okay, now that doesn't take away from what the results that they give you, but that's why a single person can go to two different companies and have slightly different results. That's the reason for that. Okay. Um, so when I say that siblings will have a different result, I'm talking about from the same company, because it's understood that you may get slightly different results from different companies. So that wouldn't be a logical comparison. That would be flawed to compare that. But I'm saying even from the same company, from the same data set, you will have a different result. They won't be exactly the same. And so I'm explaining the reason why for that. Even from parent to children. So I was just asking Mika if you still there. I know you've had your DNA tested with I think ancestry.com or 23andMe, but did any of your children get it done? And if so, were the results slightly different? And then, well, because I know it's a gap in time, but oh, she said no. Well, between parent and children, obviously, from a single parent to a child is going to be different. Why? Because the child only got 23 from the mother, 23 from the father, et cetera, et cetera, et cetera. So that's going to be different. Okay, so Sierra says, without your grandmother's recombination, yours would not be possible. So, though she may not be a DNA ancestor, her contribution makes her what? Oh, what she is, the unseen hand that makes her inherently ancestral. Okay, so that's a good so that's a point that I made. So let me just reiterate that point, is that in this conversation, and this is something that we have to understand, the context of the conversation and how and what's meant in what context. So I mentioned that earlier, that a paternal three times great grandmother will always be like my paternal three times great grandmother will always be my paternal three times great grandmother. And without her living, being alive, um, I wouldn't be alive. Okay. That's different than DNA ancestor. So although my three times paternal great grandmother is my three times paternal great grandmother, she may have not contribute any DNA to me. Let me put it better. I did not inherit any DNA from her. Therefore, she is not my DNA ancestor. And we have to make sure that that's clear. DNA ancestor. So in the general sense, she would be an ancestor in my family and contribute in my lineage, but she is not a DNA contributor. So she is not my DNA ancestor. So, we have to make sure that that's clear. And so, like I said, I'm gonna present this information again, but I'm gonna extend the conversation, which is gonna touch more on what I just said about the difference between a DNA ancestor and just a lineage ancestor. Okay, I want to talk about that difference and how and the implications of um, the influence ancestors have on the living. Just to give you a teaser of the conversation, is that ancestors influence the living two major ways. One, physiologically or physically, which is by their DNA being in your composition. And then two, from memory, by you remembering them, okay, and knowing about them. And so, again, in the extended conversation, I want to bring all of that up and have a good discussion about that. All right. So I'll leave it alone. I'll leave it there, and I'm gonna say peace to everybody. Thank you all for listening, and hanging out with me for a little bit. And I will definitely announce about the panel discussion, because I want to give anybody a chance if they want to chime in and have that discussion with me to be forewarned, when I'm going to do it. All right. So I'll be posting when I'll do that. All right. So I'm going to say peace, Shem Hotep. Hopefully everybody enjoys the rest of their night. And hopefully I left you with something to think about. And if you do some research, you find out something different, my inbox is always open, or, comment on the video. All right. So I would say Shem Hotep.